elimination just broke. Here's a 3 by 3 matrix A. The first row is 0, 1, 1. The second row is 1, 2, 1. The third row is 2, 7, 9. The first step of elimination needs the 1, 1 entry as the pivot. That's the diagonal entry used to eliminate everything below it. But it's 0. You can't divide by 0, so the algorithm hits a wall. Now, the matrix itself isn't broken. Our factorization strategy just needs an upgrade. A equals LU becomes PA equals LU. When elimination needs no row swaps, we get A equals L times U. L is lower triangular with ones on its diagonal and the multipliers below. U is upper triangular with the pivots on its diagonal. Let's see a concrete example. Let A equal the 2 by 2 matrix, 2, 1 in the first row, and the 6, 7 in the second row. To eliminate the 6 in position 2, 1, we compute the multiplier 6 divided by 2 equals 3. Now subtract 3 times row 1 from row 2. Row 2 becomes 6 minus 6, which is 0, and 7 minus 3, which is 4. So the new row 2 is 0, 4. Now we can write the factorization. The multiplier 3 goes into L, giving us L equals 1, 0 in the first row, and 3, 1 in the second row. U is the result of elimination, 2, 1 in the first row, and 0, 4 in the second row. Let's verify by multiplying L times U. The 2, 1 entry is 3 times 2 plus 1 times 0, which is 6. The 2, 2 entry is 3 times 1 plus 1 times 4, which is 7. So L times U gives us back the matrix 2, 1, 6, 7, which is exactly A. This factorization works as long as every pivot is non-zero. Let's return to our matrix A, 0, 1, 1 in the first row, 1, 2, 1 in the second row, 2, 7, 9 in the third row. Look at the 1, 1 entry. It's 0. That means elimination cannot proceed because we need a non-zero pivot in that position. But here's the key insight. This matrix is perfectly invertible. Its determinant is negative 4, which is not 0. The problem isn't with the matrix itself, it's just the row order that's wrong. The fix is simple. Swap row 1 with row 2. After the swap, our matrix becomes 1, 2, 1 in the first row, 0, 1, 1 in the second row, 2, 7, 9 in the third row. Now the first pivot is 1, which is non-zero, and elimination can continue, but we need to keep track of that row swap somewhere. That's exactly where the permutation matrix enters the picture. A permutation matrix is simply the identity matrix with its rows reordered. Let's start with the 3 by 3 identity matrix. Row 1 is 1, 0, 0. Row 2 is 0, 1, 0. Row 3 is 0, 0, 1. Now, to record the operation of swapping rows 1 and 2, we perform that same swap on the identity matrix. Take row 1 and row 2 and switch their positions. The result is our permutation matrix P, which equals 0, 1, 0 in the first row, 1, 0, 0 in the second row, and 0, 0, 1 in the third row. Notice that each row of P has exactly a single 1, and each column of P also has exactly a single 1, with zeros everywhere else. This is the defining property of a permutation matrix. Now, the identity matrix itself is actually the trivial permutation, meaning no rows are exchanged at all. When P equals I, the equation PA equals LU simply reduces to A equals LU because I times A is just A. So A equals LU is really just a special case of PA equals LU where no row swaps are needed. How many n by n permutation matrices exist? Think about it this way. The first row of the identity can be placed in any of n positions. The second row then has n-1 remaining choices. The third row has n-2 choices, and so on. The total count is n factorial, written as n followed by an exclamation point, which means n times n-1 times n-2, all the way down to 1. For n equals 3, 3 factorial equals 3 times 2 times 1, which equals 6. So there are exactly 6 3 by 3 permutation matrices. Here they all are, labeled by the row order they produce. First 1, 2, 3, that's the identity matrix, where rows stay in the original order. Next 1, 3, 2, rows 2 and 3 are swapped. Then 2, 1, 3, rows 1 and 2 are swapped. Then 2, 3, 1. A cyclic shift sending a row 2 to position 1, row 3 to position 2, and the row 1 to position 3. Then 3, 1, 2, another cyclic shift. And finally 3, 2, 1. Rows 1 and 3 are swapped. That gives us one matrix for every possible reordering of 3 rows. Every permutation matrix satisfies P inverse equals P transpose. Let's verify this with a specific example. Take the permutation that sends rows 1, 2, 3 to 3, 1, 2. The matrix P is row 1 is 0, 0, 1. Row 2 is 1, 0, 0. Row 3 is 0, 1, 0. To find the transpose, we flip rows and columns across the diagonal. P transpose is row 1 is 0, 1, 0. Row 2 is 0, 0, 1. Row 3 is 1, 0, 0. Now let's multiply P transpose times P and check that we get the identity. Take row 1 of P transpose, which is 0, 1, 0, and dot it with each column of P. Dotting with column 1, which is 0, 1, 0, gives 0 times 0 plus 1 times 1 plus 0 times 0, which equals 1. Dotting with column 2, which is 0, 0, 1, gives 0. Dotting with column 3, which is 1, 0, 0, gives 0. So the first row of the product is 1, 0, 0. For row 2 of P transpose, which is 0, 0, 1, we similarly get 0, 1, 0. And for row 3 of P transpose, which is 1, 0, 0, we get 0, 0, 1. The product is the 3 by 3 identity matrix, P transpose times P equals I, which confirms that P inverse is P transpose. Do a shuffle, then reverse it, and you're back where you started. Time for the complete factorization. We start with A equals the matrix, 0, 1, 1 in the first row, 1, 2, 1 in the second row, 2, 7, 9 in the third row. Notice that the 1, 1 position is 0, which means we cannot pivot on it directly. So we swap rows 1 and 2. The permutation matrix P for this row swap is 0, 1, 0, 1, 0, 0, 0, 0, 1. Now we compute P times A. Row 1 of PA comes from row 2 of A, giving 1, 2, 1. Row 2 comes from row 1 of A, giving 0, 1, 1. Row 3 stays the same, 2, 7, 9. So PA equals the matrix 1, 2, 1. 0, 1, 1, 2, 7, 9. Now we eliminate. In the first round, we subtract 2 times row 1 from row 3. That gives us 2 minus 2. 7 minus 4, 9 minus 2, which is 0, 3, 7. The multiplier L31 is 2. In the second round, we subtract 3 times row 2 from the new row 3. That gives us 0 minus 0, 3 minus 3, 7 minus 3, which is 0, 0, 4. The multiplier L32 is 3. We now have the upper triangular matrix U equals 1, 2, 1, 0, 1, 1, 0, 0, 4. Now let's assemble the final result. L holds the multipliers with 1s on the diagonal. Row 1 is 1, 0, 0. Row 2 is 0, 1, 0. Row 3 is 2, 3, 1. The multipliers 2 and 3 appear in the lower triangular part. U is upper triangular. Row 1 is 1, 2, 1. Row 2 is 0, 1, 1. Row 3 is 0, 0, 4. The pivots along the diagonal of U are 1, 1, and 4. Now we can write the complete factorization. P times A equals L times U with all 4 matrices displayed. P is the permutation matrix that was discovered during the elimination process. It was not guessed afterward. Since P is a permutation matrix, its inverse equals its transpose. Therefore, we can recover A as P transpose times L times U. Multiplying this out gives us back 0, 1, 1, 1, 2, 1, 2, 7, 9, which is exactly our original matrix A. This confirms the factorization is correct. Here is the complete framework. Start with any invertible matrix A. Ask yourself, does elimination require row exchanges? If the answer is no, then P equals the identity matrix, and we simply get A equals LU. If the answer is yes, we record the row swaps in a permutation matrix P, and we get PA equals LU. So A equals LU is the special case when no row swaps are needed. PA equals LU is the universal factorization that works for every invertible matrix. In both cases, L is lower triangular with ones on the diagonal, and U is upper triangular. Also remember that for any permutation matrix, P inverse equals P transpose. This is always true. Every serious numerical library, MATLAB, NumPy, LaPack, uses PA equals LU internally. Here's why this matters in practice. Rounding errors can make a pivot effectively zero, even when it's technically non-zero. Whether we encounter an exact zero pivot or a near zero pivot due to rounding, the solution is the same. A row exchange is needed. PA equals LU ensures stability through partial pivoting. Let's summarize the three key takeaways. First, PA equals LU works for every invertible matrix, no exceptions. Second, P inverse equals P transpose, meaning undoing a permutation costs nothing computationally. And third, partial pivoting ensures numerical stability in real-world computations. These three matrices, PL and U, capture the complete elimination story for any invertible matrix. PA equals LU.